And that's a proof that I think we proved like way back in like Math 8. But what that means is if we think about the unit circle is 1 of radius, right? So the unit circle's actually got a diameter of 2. But we could scale this circle any size we wanted. We could scale it smaller. Keyboard, get out of here. We could scale it smaller. We could scale it bigger. And the size of this angle doesn't change. Well, Katie Ann's judgmental. I'm glad some things haven't changed. So the angle, just like Katie Ann's judgments, stays the same. Right? Regardless of the size of the circle. Now, if my circle's not centered, that does mess things up. I will admit, it does mess things up. But let's assume that this was centered. So now, if we pop over here, this distance is our radius of size we don't know. It's just R. This distance, sorry, this is meant to be color-coded. Did I put it in the slides? No, I did not put it in the slides. Yeah, I can't print in color. We don't have a color printer working right now. At least not down here. There might be one upstairs that I need to go check. But this is meant to be color-coded. So what I would like you to do is either with highlighters or at least like make sure that you notate that these are all points. Please label each R around the circle. You should end up having 7 R's written if you include the middle R of the radius. And that is because we know the circumference of 360 degrees of rotation is a distance of 2 pi times whatever our radius is. Everything has to do with the unit circle. Yes, yeah. Easy answer is yes, but I like to say everything comes back to the unit circle, because it kind of does, really.
Does it make sense? Because if the unit circle of the radius would be 1, that would mean that 2 pi is 6.24.
Well, 2 pi is equal to 6.24. So if your unit circle is 1, then yeah, your circumference is 6.24, approximately, right? So that's not a perfect. So, but that's not like 6.24. First off, it's not perfect, right? It's approximate. And second off, it's not like it's a decimal. It's not like 6.25. That would be nice. So we pretty much always talk in terms of pi. Now what that means is if we split this up by radians, each distance of r, the tiny little bit out here is going to be approximately 0.24 radians. Yeah.
So does that mean that, like, 360 degrees is equal to
2 pi
pi radians?
radians, but yes. So guys, a radian is your radius. That's really it. A radian is the same measure, like same length as whatever your radius is. And I see the perplexed faces. The reason we use it is we're talking about curved distances, right? Not straight distances. We're talking about curved distances. Now, because I was trying to figure out like a connection and everything else, I went and asked my buddy Randy, who is a draftsman by profession. He gets paid to draw like buildings and other things. And I was like, dude, do you use radians like in the real world? And he's like, yeah, of course I do. I was like, all right, how? He was like, well, that's kind of hard to explain. I was like, try, right? Like, try. And he's like, well, sometimes radians are just better. I was like, what do you mean by that? And he goes, it's like degrees are kind of complicated. Radians in certain situations are less complicated. And I was like, well, like, give me an example. And he's like, I mean, when I'm like completing the circle or completing the square, and he started like going down this rabbit hole, and I'm like, oh, well, my students don't know what that means, and I barely know what that means. And he's like, well, what I can tell you is radians are useful. And Mr. Smith and I were talking this morning, and we kind of said the opposite. Mr. Smith and I have never used radians in our real adult life, ever. But Mr. Smith and I are teachers. We didn't go down a heavy math field. I mean, I have a degree in mathematics, but I did not become an engineer, right? I did not, go the heavy math field. You will need radians if you do any, math field, especially anything involving calculus. So at the end of the day, I really just need you to believe me that it's important to learn. I mean, you could also just look at it as, well, at school, I just have to learn this, whatever. But I'm trying to make you believe that, yes, there are real applications for this. One of the reasons being, they're just easier to split up sometimes. Because when we think about degrees, there are 360 degrees in a circle. That doesn't split up all that great. Okay, divide by 10, 36 works. Divide by 10 again, 3.6. It's not terrible, but it's not great, right? So, I think it was the Pythagoreans, but I should have looked this up, so don't quote me. We can start to talk about arc length in terms of radians because we don't always know the scale. So one of the other things that Randy and I were talking about was when he's doing a drawing, he doesn't know what scale the people are going to want it in when they print it. So guys, think about this. Excuse me, you draw a drawing, put it in the computer, and then you can zoom it in and zoom it out, but when you go to print it, it has to be able to print. So you don't actually know, to be able to measure with an actual measuring device, that will be accurate. So we have to use scale factors for things, right? So radians are how we can, yep, that's exactly what I was about to do. Radians are how we make life easier because, and I'm going to just straight up give you the, most important critical thing of this entire lesson right here. 180 degrees is equal to pi radians. Because like we said, if our radius is 1, then that arc length, that partial circumference, is actually just 3.14. Literally, it's just pi times whatever your radius is. But that's for half the circle, right? So we could also say 360 is equal to 2 pi. We could also say that. That would be totally fine. Take a moment, now that we know this conversion factor, to try this problem up here. Well, I've already kind of given it to you. Try the next 3 problems down below. Here's a nice little trick, though. Can anyone tell me what happened between the angle measure they gave me and the amount of the circumference, the fraction of the circumference that they asked me for? So let's walk through this problem together. The angle they gave me is 3 pi over 5. I know that's a little over half of pi, right? 3/5 is a little over half of pi. So I can imagine half of pi would be a 90-degree angle, right? So a little over half of pi. I need to figure out this arc, what portion of the circle is the arc. Okay, I know it's less than half. I know it's bigger than a fourth. Well, to figure out a portion, we set up a ratio, right? So we compare the arc to the circumference. Well, if the arc gets 3/5 of pi, and the circumference normally gets 2 pi, why did I put this over 1? Yeah, because now I have a fraction divided by a fraction, which I can keep, change, flip, and do fraction times a fraction. When I keep, change, flip, and solve this, well, the pi's cancel out. I get 3/10. Oh, I just get rid of the pi and double the denominator. Is a nice little trick we could use. You don't have to. It's just a tool, right? It's another tool available for you. So knowing that we can use pi equals 180 degrees as a conversion factor, try to convert those next 3 radian measures to degree measures. So take a moment down there at the bottom of the paper, below where it says arguably the most helpful conversion. Hopefully you have this conversion written down. So what we're doing is literally just converting. Have you guys ever heard this called stoichiometry? So I think stoichiometry is actually a branch of science where you do unit conversion. But we're just going to take what we start with and multiply it by our conversion factor. So if what we start with has pi, we want to get rid of pi. I can use my conversion factor as 180 over pi or pi over 180 because these values are equivalent, we said. This is 1, right, guys? Our conversion factor, any conversion factor, is equal to 1 because that's what makes it a conversion factor. The 2 values are equal to each other. So this is really multiplication by 1 just to change our units. So our units was pi radians. Like pi is part of the number. Radians is really our unit. So we put the pi on bottom, we do the multiplication, and we get 160. Any questions on that one? If not, do the next 2 on your own. They should actually be kind of easy. Because 17 compared to 18, oh man, 18 is kind of like 180. Okay, Amar, explain to me why that did not help you at all. If pi is 180 degrees, is this going to be more or less than 180 degrees? Well, less, right? Because it's less than 1 pi. This is 17/18 pi. It's almost 1 pi, but it's not quite there. You should get 170 degrees. Yeah. Yeah, but, well, yes, but what you're actually doing also involves the pi's, and the pi's cancel each other out. So as long as you know that, yes, what you're saying about the math we actually calculate, yes, you're right. But make sure that you think about the pi's are actually there, they're canceling each other out. I just don't want you to accidentally, when we convert back the other way, forget about your pi. You know what I mean? Because we have to bring pi back when we convert back the other way, from degrees into radians. And then 5/12 pi, well, again, it's less than pi, so it's going to be less than 180 when we do the math. Absolutely what you just said. It's almost like you were reading my mind. We don't actually have to think about the pi's. You could write down 5/12 pi times 180 over pi, or if you think about the fact that the pi's are always going to cancel, just take your fraction and multiply it by 180. Very astute observation, Kaylin. I appreciate that. Any questions from the front? I caught myself from saying flip to the back. I used to. That's a baseball bat. Baseball tryouts are happening right now. You are correct. What an astute observation, Katie Ann. On the back, we're doing the same thing except going the other direction. So when we start with degrees and we're going into radians, we just multiply by pi over 180. But remember, that also brings in the label of radians, because it's actually pi radians is equal to 180. So I don't know why this won't zoom or focus. There we go. So remember, we have to bring in not only the pi, but also the label of radians. Please try that for the next two on your own. It's kind of what? Oh, it's kind of rad. Ha ha ha, I see what you did there. Hey, Amar, you can step into the hallway to blow your nose if you need, and then make sure you use hand sanitizer. You can bring it back in to throw it away in here, but just you can blow your nose out there so you're, you got space. So, Kaylin, have you figured out a shortcut on this method? Because if we remember a certain, okay, at the end, I just whatever, then the math is pretty quick. Multiply by 1. Oh, well, that's when the fraction can't be reduced. So remember, we always want to reduce if we can. Essentially, the shortcut you could think of here is we're just dividing by 180. But then our label becomes pi radians, so that's not really technically quite true. Pi is not part of our label. Remember that pi is part of our number. So there is the shortcut of you can just divide by 180, but remember, you're actually multiplying by pi and dividing by 180. Yes?
When we go back into everybody together, are you gonna assign people?
Probably not, because I still like Khan, because I can go in there and see what you guys have worked on, how many times it has taken you. It gives me a lot of really powerful data. And we're trying to finish up all of our standards before the state test, because even though Worthington passed a resolution that says they don't think we should be testing, we still are. Our school board has said, we do not think we should make the students take the test this year, but the state is saying, well, we don't care, take the test. So if we think about that shortcut, we essentially take the degrees we had. Notice I don't have my degree symbol here anymore in my answer. The degrees we had, we divide it by 180, and we tack on a pi, and we make our label radians. But we always reduce if we can. So 35 and 180 can definitely be reduced by 5 for sure. I do not think that can reduce any further. So you could also write it as 7 pi over 36, or you can write it 7/36 pi. So for 100 degrees over here, it becomes 100 over 180, and a pi, and a radians. Now we know the zeros can wipe out. 10 over 18... 5/9 pi radians. What? It probably has more ink, and it is probably just, you know what I mean? We could do a little test if you want. There's a dot of the pink. There's a dot of the green. I mean, it just looks like the pink writes a tiny bit heavier. Okay, then I'll keep writing in pink. So now we come down to where we have pictures. All right, what is the measure in radians of the central angle theta in the circle below What are we supposed to do here? What do we know? Who can help me out with this? We know the arc length of the partial circumference. We know the radius. Remember, if it's the diameter, they will put the number in the middle of the circle. Like the 8 would be like right by the dot if that was the whole diameter. Well, a radian is the equal length as the radius, yes. Ah, why? So you can flip your paper over if you're trying to remember what that exactly is. The circumference is normally double the radius times pi. Right? But normally we write it 2 pi r, but it's double the radius times pi. So the normal circumference here would be 16 pi. So knowing that, I know that this 8 pi compared to 16 pi is half of the circle, meaning that my theta is, but in radians, oh wait, it's just pi. No, say it again. This is why I did that. Because I want you to say that again, but when people will actually listen. Because now we see what happened. Say it again. What's it? It being theta. Thank you. Theta. So what Alina's saying is that theta is the arc divided by the radius. You tell me. I don't know. Why? Why does this work? Sometimes. Because wait. So up here it's 5 halves? Like you said, just take the arc length and divide by the radius. So this is just 5 halves? Does this work? Well, that'd be 5 halves radians, right? So I need to make sure that I'm thinking in radians. Well, 5 halves is 2.5. What? Guys, if I extend my radius out, and we say that a half circle is pi radius, what is pi? Pi is like 3.14, right? So if if the arc length came all the way around, then our theta over here was 3.14 radians, right? Not exactly, right? It's exactly pi. But so if this is 2.5, well, that makes sense because it needs to be less than pi. What's up, Miss Allie? Nothing. You just wanted the kids to. Do you remember anything about arc length and radians, or do you just want to run the other way? What'd you say? Doesn't Miss Allie's hair look sweet? I dig it. She just changed it this week.
Sometimes I like to do other things with my hair. I got a 20. I was in the 26th percentile on the math GRE, Mr. Hudson. So.
What's percentile mean? What are you talking about?
I don't know. That's why I did poorly. Wait.
I'm giving Miss Allie a hard time that if she is talking about percentile and doesn't know what percentile is, it is ironic.
She didn't have a teacher like Mr. Hudson.
Oh, well, thanks.
She was a senior in high
By then the apathy is too strong.
By then it was gone.
So over here, guys, when they tell us that the arc length is 3, we know, or sorry, not arc length, the theta is 3. This is 3 radians. Right? Because even though we normally use pi for radians, we don't have to. No one said you absolutely always have to use a pi number in your radian measure. So, if we said the theta is equal to arc over radius, and we know the theta is 3, and the arc is s, and the radius is 8. Yeah, okay, so s is 24. Do we want to go back and talk about why this formula actually works? Theta is a measurement we have created. It's like a scale that we created that when we are discussing it in radians, guys, remember how we calculate radians is a ratio of circumference compared to radius. So arc compared to radius is the same thing. It's how much of the circumference compared to the radius tells you how big we've opened. So if it's 1, you've opened the exact same distance as what your radius length is. So the curved distance, if you have opened a theta of 1, that gives you 1 radius. So if you need a reference back to that, that's what I have right here. And where on Tuesday, got a little frustrated because you guys wouldn't stop talking. So that's what this is trying to show us, is this is 1 radian. This opening right there is 1 radian. So if you want to go back and remind yourself of that, and that means we've opened the rotational distance equivalent to the radius. And that's approximately 58 degrees. It's really 57 point something. So, now I want you to take, I may actually just give you like 5 minutes, because I don't know how much time we have left. I want you to try these on your own. I think we know enough at this point to be able to do the area of a sector. So you are trying to find the area of the shaded region. Oh, I got tons of time. Look at that. Don't worry, guys. These notes have a different header. I did not just keep naming things circles and radians. Well, not so. How do you normally figure out the area of a circle? Pi times radius squared, right? So then how we figure out a portion of a circle is to do the proportion of the whole circle, right? So to find the area of a sector, we're going to take the portion that we have times the pi times radius squared. So the first thing we have to do is figure out what portion we have. Okay, up here, if I have 135 degrees, that's 135 out of, what should I have? If I had the whole thing, I would have 360. My radius is 4. We're just going to do that. And we use our calculator. Because I'm never going to ask you to do something like that in your head. Now, a lot of times, guys, especially if your areas come out messy, leave it in terms of pi. So what I mean by that is when we type this into our calculator, $18.84955592, not nice. You know what's a lot nicer than that? 6. So if we leave it in terms of pi, we just get 6 pi. We gotta have a label. So centimeters squared. Does this process make sense? We should what? I still can't hear you. I was about to have you do it on your own. Do you want to do it? Wow. That was a real quick no. That's like you knew I was going to ask and you were prepared to say no. Like just waiting to pull that trigger. Ooh, the last one tells us what the area is. Crap, how are we going to deal with that? How am I going to do that? Didn't work. Only going to count the ceiling tiles. When you get bored with that, count how many dots are on each ceiling tile. Yeah, what's the ratio of amount of ceiling tile that is white versus amount of ceiling tile is like dotted? In here? That's more than I expected. What's our area of the sector over here in the middle? Yeah, that's what it asks us for. In the middle. Yep, 70 pi. Is that what you said? So, what would our area be if the circle was full? 49 pi, right? So then, since this area is a third of that, then okay, that's a third. So how many degrees is a third of the circle? 120 degrees. Easier. Put an ER on the end of that because we don't like calling things easy. Sure. Did you research it?
No.
Then I don't want to hear anything else about it until you research it on your own. And if it doesn't have its own name, couldn't we just like make one up? I mean, guys, everything in math is pretty much made up. What's that?
Why do your S's look like 5s?
Why do your 5s look like S's?
I just got confused. I'm like, wait, why did it say 5 is equal to? And then I realized it was an S.
Yeah, you can always double check, but I try to avoid S's for that reason. So, yeah. All right, so my goal is between today and tomorrow we get done with this next worksheet because then Monday is Blue Group, right? And then they will do this worksheet and we'll actually be synced back up. Like, because we're a tiny bit off sync right now, but this should work. So you have this and a little bit more on another one of the worksheets, but we definitely need to remember this to be able to dive into our inscribed angles work. So everyone make sure you're looking at inscribed angles and shapes. One of the ways that Randy's my friend who's a draftsman, was telling me radians do get used is a technique called complete the circle, which at first I was like, I know completing the square, right? We did completing the square back in what year? Quadratics, right? Back in my trinomials are like x squared, that sort of stuff. We did completing the square with quadratics. But, oh, I can't move this from here. So, if you were at a site survey, and a site survey is when like you're trying to draw out what exists, and have you ever seen those guys with like lasers and big sticks that are like marked with like heights and stuff, and they're like looking through things and like taking pictures? Those are surveyors. Those are land surveyors.
Laser level.
Yeah, laser level. Super fun, very expensive.
I've seen them.
So, if you were standing here, shooting your lasers this way, and you intersect a round object, what you actually know is that the angle created right here is half of the arc measure of the angle created from the points that it hits. Now that rule is up at the top of your page. That is what that rule tells you. The other thing we know is if somebody else was standing on the very center of that rounded object, that circular whatever, this angle is equal to the subtended arc length. I don't like that word. I don't know why Con uses it so much. Subtended. It's in like a bunch of your activities right now. All it means is like the arc we hit, right? So this is an inscribed angle because it's in the circle. This is a central angle because it is central. So we have inscribed angles, central angles. They both subtend the arc because they hit it, right? They like run into it. So make sure you're double checking if they're giving us angles or arcs. They tell us angle ABC is 124. Meaning that this arc from A to C is 124. Meaning angle CDB down here would be how big? 62. And then 23, 35, and 20? I don't know what you're relating about those numbers. Well, yeah, that was intentional because this is the one I do for you, and then this is the one I tell you do on your own, right? So it's very similar. You should be very in tune with it. And then do the other. Really, let's do 5 minutes. Try to finish the front of this worksheet. It should be fairly quick. When you're ready to check, look up at the board. When you're ready to check, yeah, notice I didn't move my paper yet. Obviously, the bottom three get a bit trickier. Any questions on those first three? All right, keep working. I'm going to give you some time on the bottom. Since ADC is 23, can I put my 23 there? Crap, why? So wait, what should go here? Oh, double! Because it's inscribed, the arc, it's doubled the angle. So that's not 23. It's 46. So that's the mistake I hope you do not make now that I've pointed it out. Keep it in your head of, am I inscribed or am I central? And make sure you like double check yourself. So this is inscribed. It has that 1/2 or doubling relationship. So the arc is double. But then ABC is what kind of angle? Central or inscribed? Central. So it is equivalent to the arc. So we do not half or double again. We just use that value. Could you tell me what major arc CDA is? Yeah, right? Because it's like the complement, but it's whatever makes 360, right? Did we ever figure out if there's a good word for that? Well, I didn't try, but because I didn't look it up, I need to see it written. But yeah, it's whatever that word is, right? That makes 360 together. Could you tell me what arc CD is? Major or minor, I don't care. So are you clear on ADC being this angle right here? Then if we reference back up to here, an inscribed angle is half of its subtended arc. So Alina, we're going step at a time. Are you comfortable